No sound. And now, okay. Thank you again now with sound. And thank you for coming. I have 2 lectures today and 2 lectures tomorrow. And I know today is Saturday, tomorrow even Sunday, so the subject will be different. So I understand that somebody come only one day, somebody never. So I will try to do my best that subject today, subject tomorrow will be somehow related, but not precise. And my subject is coupling conformal field theories. This is rather vague scene. I'll concentrate mainly on one example. And during this example, I try to say what is it and how to use it and so on. But first, I have some sort of plan. Maybe I'll also give it at some point at the end. But at least I will use some labels. So now into the first point of my plan. And since I'm talking about coupling conformal field theories, or in more mathematical language, vertex algebras, I will try to give some definition. And I will not give definition of the vertex algebra, but I'll concentrate on 2 main examples of vertex algebra. First of them is a affine SL2. So not sure that I need to recall what is it, but I just fix some notation. So I will denote generators of SL2 by En, Hn, Fn, and also central generator K with the standard commutation relations. But sometimes I will write some formulas, try to write some formulas in a bit another manner, and that's why I changed notation from this to G plus, G0, G3. It is the same, but G minus, but more physical. And even more, sometimes it will be more convenient to work in orthonormal basis with respect to Killing form. That's why I go to G3 and G1, G2, and this is not the same basis. G1 is a sum of them and G2 is a difference, something like this. It is orthonormal basis. And again, I can write index n. Okay. The concerning representation of this algebra, I will need highest weight representations. So highest weight representations. It means that we have highest weight vector v such that En of v equal to 0 for n greater than or equal to 0, and Fn of v equal to Hn of v equal to 0 for n greater than 0, and H0 of v is equal to some number which I usually denote by the same letter H. And K and V equal to K. This, so all of these are equations for highest weight vector. And if we consider representation which is freely generated of this highest weight vector, this is Verma module, and I denote it by VHK. Verma model. And if I will need to consider its irreducible quotient, I will denote by L. HK. For generic values of h and k, whatever it means, the Fermat model is irreducible. It becomes reducible for special values. For example, the simplest example, if h equal to 0, then and k generic, then this irreducible model is a quotient of the Fermat model by one singular vector, which obtained by action of f0 on the highest weight vector. This representation L0k has a structure of vertex algebra. Okay, let me use another blackboard. So, I mean, I will not go to define what this means, but it means that, but in words, it means that for any vector in NLK, I can assign a field y of v and z. Field. This is a power series of y of vz, if you want, sub n z in power minus n. And all this and these y's are operators acting on something. So in this definition, just act on this L0k, but below they will write on representations. And
so, do you make any assumptions on k? Or?
Here I said that k is generic. Actually, we'll need two cases. K is generic. Generic, for example, means irrational. It is written here, but at some point, accidentally, I will use k equal to 1. But and these y's can be constructed using the fields E of z, f of z, h of z, which are just sum of en z in power minus n minus 1, and similar for other, sum of hn z minus n minus 1, constructed from. And by word constructed, I mean that I take their products, their derivatives, and that's all. All fields which you have in this vertex algebra are given in this manner. So if you don't know what is vertex algebra, but know something about affine algebras, and you can imagine such fields, then you know all we need here. Okay, and this is what I need for the start for affine SL2. And my second main example of vertex algebra, at least for today, will be just Virasoro algebra. As usual, Virasoro algebra generated by Ln and central element C with the commutation relations. I hope so. One can define similar the highest weight representation of the Virasoro algebra. So they are the highest weight vectors are should be annihilated by ln for n greater than 0. L0 should act on V by some number which I denote by delta, usually. And as central element will act by number which I denote again by C. Fermat models I will denote by same letter, but with another notation for indices, V delta C. The Fermat models. And similarly, L delta C will be irreducible quotients. Again, for generic values of delta and C, Fermat modulus is reducible. For some for special values, there is well-known cut theorem which says when this model is reducible. I will need some details probably soon, but for the beginning, let me state that for generic C and delta equal to 0, the irreducible model L0C is a quotient of the Fermat model by the submodel generated by action of L-1 on highest wave vector. And this, okay, let me go here. L0C again has a structure of vertex algebra. Again, it means that for any vector in this representation we can assign some field, and again there is some sort of reconstruction theorem which says in terms of which field in terms of which basic elementary fields all these fields are constructed. In this case the basic field is T of Z, stress energy tensor, which is given by formula okay, let me write here. And all fields okay, so these two vertex algebras are, I think, the main examples of the vertex algebras, and there are actually some relations between them. And one of them is given by Sugawara formula. One can for SL2 hat one can define T where the stress energy tensor in terms of the fields E, F, and H by the formula I use the notation for normally ordered products without explanation. I hope if you don't know, you can just ignore it. It is. I hope it's not so visible, so it will be easy.
You can see them, they can was anything.
Okay, so I think we have a lot of dots here, so this will be easy. And the statement is that consider components of this Sugawara tensor denoted by ln Sugawara, them satisfy Virasora relations. I don't know, satisfy Virasora algebra. With a central charge C equal to, I believe, yes, 3k. Yes. During talk, I plan to write some formulas. To be honest, some of them could be not really correct. But on this formula, I believe, and many people obviously can correct it. For example, for k equal 1, special case, this should give c equal 1. So this. Yes, yes, and have to go to infinity, and so from the critical level, it should have. If k goes to infinity, it should go to 3, the number of fields in SL2. So there are several reasons to guess at formula without calculations. Okay. What? Let me introduce a bit more notations for the Virasora case. It is sometimes convenient to write to parameterize Virasora representations not by the delta, so-called conformal dimension, and central charge C, but somehow solve quadratic equations. So write C in form 1 plus 6b plus b inverse squared. The answers, and then write delta in a form like this, b 2 squared minus p squared. So come from delta and C to B and P. This is just convenient to state in the answer. For example, if you ask me, if you know about minimal models, and you know that it has happened for special rational C, but what kind of C it is, say, it is not easy to say. It is easy to say that this happens for such C, that B square is a negative rational number. And that's it. This such. So C is also should be rational, but not any rational number correspond to C correspond to rational B. So in terms of B, it is easy to give an answer. And I will really abuse notations, and if I mean this parameterization, I will use notation V PB, L PB, and so on. Okay. As I said, there are many relations between these two algebras, SL2 hat and Virasora, and I'm not sure, I probably will need several, but now we come to the second point of the plan, which corresponds to so-called cassette construction. This is concrete relation. Consider two Virasora algebras. To do SL2 algebras. SL2 hat plus SL2 hat. One of them of the level 1. I don't know, let me write it as an index. level, and another of the generic level K. Then there is of course, there is an embedding of SL2 of the level K plus 1 into this direct sum. Word cassette stands for the answer for the following question. What commutes with this diagonal SL2 K plus 1 in this direct sum, SL21 and SL2K?
In the universal envelope.
In the universal envelope, better to say in the product. If you take product of the two vertex algebras, then we have embedding of the vertex algebra, and what commutes with this?
Something in the local completion.
Something like this. In this case, the answer can be in this form. Cassette construction probably was introduced 30 years ago by physicists Goddard, Kent, Olive, and the answer is given by the following. One can construct one more Virasoro algebra, energy momentum tensor, by the following formula. T1 by not difficult computation, one can show that this thing indeed satisfies Virasoro algebra and commute with this SL2 K plus 1. And the central charge C is equal by C of B, which I denote in such manner. So C of B is this function. And B is such number that B squared I think in the original paper by Goddard, Kent, Olive, they study the case where K is a positive integer number. And in this case, these representations of course, are more difficult than quotient by just one singular vector. By more difficult, I mean we have two singular vectors. They're integrable, and they're also interrealizable. And this B, which we have here, then correspond to a very special representation of the Virasoro algebra, again interrealizable, and correspond to minimal model. These two numbers, K plus 2 and K plus 3, exactly parameters corresponding to minimal model. But today I'm talking about generic K, not rational. And so I use this notation, but do not think that this is just generic one. And let me state what happens with the representation as some sort of proposition. If we take a vacuum representation of this vertex algebra, L01 tensor L0K, one can ask what will be the decomposition of this vertex algebra with respect to these two commuting of this representation with respect to these two commuting algebra, diagonal SL2 and Virasoro. And the answer is it will be the direct sum over integer So here I'll use one more notation, which I'm going to explain. So I denote all reduced representation by letter L. So it is natural now to think what of this representation is a representation of the Virasoro algebra, and what of them is it clear from my notation which of them is a representation of Virasoro and which is a representation of the SL2 hat. I don't know. Vanya, do you know? No. Okay, physics intuition says that Virasoro should depend on parameter B. So this is the representation of the Virasoro. Let me draw it in here.
Different kind of basic equation tells us that the notation should be more clear.
Otherwise, we need some more time to explain it twice. Otherwise, we will struggle. So this Virasoro, and this is affine SL2. And again, you can see here's a level, k plus 1, as should be for diagonal SL2. So this representation is already, this notation hopefully was already defined. So this representation of affine SL2 with a level of k plus 1 and the action of h, highest weight, is equal to 2n. And 2n, you see the integer non-negative number. So we have special representations which are again quotient by the Verma model by one singular vector. Not just f0 as here, but f0 in the power of 2n plus 1. And this representation are also special. They're not, this notation 1, 2n plus 1 stands for the following: p mn. So delta 1, 2n plus 1 is a delta of p 1, 2n plus 1 b. So this notation for and this p actually can depend on two integer numbers, which is one of them is 1 here for some reason is and probably this is the time to recall the theorem by this called, I think, Katz's theorem. Or should they call it Feigen-Fuchs theorem? I don't know. So there is a theorem that representation that Verma model MPB is irreducible. Yes, this is V, indeed. Why indeed this V is irreducible if P is not equal to P mn for mn both positive integers. So for example, if m and n both equal to 1, p11, then from comparing several formulas on the blackboard, you can see that corresponding delta is equal to 0. And this corresponds to vacuum model, which is written somewhere on the blackboard. And vacuum model also appears here. This is for the sum for n equals 0. All other summations here.
The pair of numbers 1 and 2n plus 1 is not delta and c.
1 there in brackets, you see. So these two numbers parameterize parameter p. And this b corresponds to central charge. So this is this notation L mn B is the same as LPMN B. But I'm trying to erase all, for example, letter P is not necessary for, so all information hidden in these two numbers, as well as here's this number to n. Okay, so this theorem says that for us that this representation which appear here are quite special. This reducible rotation obtained by quotient of Fermat model, I can even say you that if B is generic, I can add one more statement to the theorem. If B is generic, then LMN, LPMN B is a quotient of Fermat model by the submodel generated by one singular vector, and this D is special operator of degree Mn. If Mn then all both equal to 1, this is just L minus 1 on V. And if M equal 1, N equal 2, this is something like L minus square plus L minus 2. And generically, this is some operator. There are some formulas for them, but not so explicit in the SL2 case. Okay, I think I'm already speaking like half an hour, or maybe even more. And probably it's time to recall the title of the talk, Coupling of Conformal Field Theories. I said that I will use either word conformal field theories or word vertex algebras, so this is okay, but where is the coupling? You can ask me. And I'm trying to say that coupling is here. So what we have here on the right side. First summand here, we have a product, which in my notations here is L11 k plus 2 over k plus 3 times L0 k plus 1. This is a vacuum module for just tensor product of the Virasoro algebra, or if I write Lie algebras, I write direct sum, and SL2 hat. This SL2 hat have level k plus 1. And this Virasoro algebra has central charge related to this the level of this algebra. So these two algebras, we have direct sum, but they somehow interact. They interact through the central charge. And this makes possible to extend this tensor product by some other representation. We see that we have here full direct sum. These summands, which correspond to, as I said, special actually reducible representations, will be local, will have integer highest weight, and all the sum will have the structure of vertex algebras. In this case, we know this because we have interpretation of the left side. Left side is a tensor product of vertex algebras. It's okay, it has the structure. In principle, you can try to cook up such sort of example without good structure as a tensor. This fact that the left side has the structure of tensor product is actually some sort of coincidence. So it can happen that you can take. So what I mean by word coupling. We have vertex algebra 1 vertex algebra 2, take their tensor product, and extend by something. Something which we should add should be tensor product of representation of first and second algebra. And of course, in order to this have some meaning, this should be some special representation. So in this case, the special representation which are reducible. Extend by special. And let me write this in, at least in some formula. The fact that it's possible to extend, for example, means that the highest weight with respect to total Virasoro algebra of this additional representation should be integer. Or if you agree on superalgebras, it can be half integer. If you're more polite, it can be fractional, 1/4. It's sometimes we can deal with something like, so half integers means we have some sort of fermions. Rational numbers can be interpreted as some sort of parafermions, but no square roots of 2, nothing. So in this case, for example, I take the central charge of this. So I take highest weight. This is delta of P1 to n plus 1. In B, which my notations 2k, k plus 2 over k over 3, and add highest weight of this representation. I can recall the formula for it. The best way to recall it here, so corresponding, if I take have a Verma model with the highest weight h in central and level k, then the corresponding delta is equal to h times h plus 1 over 4k plus 2. Anyway, some number. And so here, delta of corresponding to n k plus 1, and these sums are integer. Actually, non-negative integers, I think. Yes. So this is if I take start from just Virasoro generic central charge and cell 2 with generic level, and take the high conformal dimension of the highest of the corresponding to reducible representations, interesting representation, then their sum will be again some sort of generic. This is some sort of coincidence, of course, which we know in advance since we start with something. Okay.
So this extension is you add extra current.
Yes. Okay, I'll try to use only these two blackboards. I don't know how. I hope they're more visible, so I start erasing. If you like representation theory, maybe this is okay. This is probably natural question. But if you don't, or even if you like, it's natural to ask why do we need all this? Can we apply it for something? some non-trivial application came if we try to compute something in both sides. Easy application is just calculate characters. And this is indeed quite non-trivial, but not in this case. If I start from the integer k and write the corresponding relations here the sum will be finite, the representation, the character will become some modular function, will get some identity as a result. For generic k, the statement about characters is straightforward. So instead of characters, I need to calculate something more difficult. Characters is just the trace of some Cartan element. So in this case, it will be something like, what am I notation? X in power trace of x in power h0, z in power l0, something like this. I can calculate trace of something more difficult element, and actually I can apply some vertex operator before, and this is why I will speak about. So and in that I will obtain some relation on so-called conformal blocks. In order to state this relation, I need to define vertex operators. Okay. We came to the third point of my plan. There are different, but actually equivalent ways to define vertex operator. I'm not sure which of them do you prefer. I'll write. So one is the following. So before I need to define one more type of representation of SL2 hat. So I start from the defining vertex operators for SL2 hat. I already introduced above the highest weight representation. I need one more type of representation of this algebra, so-called evaluation representations. Probably let me define it in some formal manner. So if I start from V as any representation of just not affine algebra SL2, then I can consider the vector space V of W inverse power series and define action of, and there is an action of the SL2 T inverse on this space. So SL2 acts on V. What?
Why one variable is called W and the other is called the same?
They're the same. Because I will have many W's, but T is somehow is a part of SL2 for me. But maybe easy explanation is I have bad notation. This representation of the current algebra, you can write here for power series, and you'll have power series here. If you think about this as a representation of the affine algebra, then the corresponding level is just equal to 0. So we have all levels representations. And if we have such definitions, then vertex operators. So okay, let me write again. Vertex operators are just maps from 1 highest weight representation to the tensor product of another highest weight representation of the same level times some evaluation representation. So and this has level 0, the levels on the left side and right side are the same, so such operator could exist. Phi is a intertwining operator. This is V. This is V, yes. You can rewrite this in components. So for example, if this representation V, if some uj form a basis in representation V, then you can write phi you can write phi let me write here phi of W. So, at least formally, phi of W applied to some vector. Without it doesn't matter. Applied to some vector V as a sum of phi j of W V tensor uj. Or if you want to be more accurate, you can write it as a sum of phi j case component applied to k tensor uj w in power. Okay, here written k, I don't know if it's correct. Maybe it should be minus. Okay, in my paper k, maybe some sign. I don't. Maybe I lost some sign. So this uj times wk are form a basis here. Actually, this operator acts not on this tensor product, but on some completion. Since here phi the sum in all examples are actually infinite. But I will ignore these problems. The fact that this operator is intertwining can be written more formally like equation on this operator phi j. For example, so phi is intertwining. This is closely related to the fact that this is the same as write that, for example, commutation relations of where this C are, where is some color, structure constants of a representation V. And this GA is any generator of Lie algebra. I said that I will use G1, G2, G3 for SL2 or G plus G minus. Just not to write the formula, one formula here, not to write three formulas for A, F, and H. Probably there is some sign here, but let me ignore this. If you like language of OPE, then this is written in the form J of Z of phi J of W is something like CA J prime G phi of W over Z minus W plus normally ordered product this is all equivalent. It's just reformulation.
There should be a delta function on the right hand side. There should be a delta function on the right hand side in the commutation.
This would be delta function. And if you remember, if you want to write relation not in terms of the generators of the affine algebra, but in terms of the Sugawara or the Virasoro, which is Sugawara algebra, then you can write. This leads to some sort of differential equations, for example, like this. And this is equal to 1 over k plus h, k plus 2, maybe 2 also here, maybe not, sum of normally ordered product. This is a consequence. So we can express L0 and actually any Virasoro generator of Sugawara algebra in terms of G, and then somehow substitute everything and compute. And you obtain the equation, which is in particular can be written as a derivative of this function phi, this operator phi with respect to W. Tilde means some rescaling, that phi tilde of W is some W in power delta phi of W. This rescaling is convenient for something.
There should be structure constants in the last line.
Should be some structure constants, yes. Here should be prime, here should be G prime, AG. These equations, or some close cousin of the equation, could be called as a operator Knižnik-Zamolodchikov equation. If you write conformal block for this algebra, and conformal block is nothing else that just the matrix element of the product of vertex operators. Matrix element of here should be highest weight vector VH1, then we'll have some, so assume that we have a sequence of this vertex operators, so VH1k, first phi1 to VH1k tensor V. Assume that here I take Verma model. Page 3. I have problem with notations. H3 of and so on, and then you pick some vectors or covectors here and on the right side. Then you can compute matrix elements. So for simplicity, you can take the highest weight vector here and highest weight vector in the end. Let n be something v, h, n, k, hn plus 1, k, tensor. And here will be many evaluation representation. N's representation, which depends on parameter wn. So on. In my notations, first time from h2. Then this matrix element of the vh1, h n plus 1, phi n, phi 2. Such sort of matrix element, and if I pick concrete, how to say? There are two ways to say. I can either pick concrete basic elements in these spaces, or better to say in dual spaces, and this will be, and for example, the highest weight vector here, and vector here, and also covector here, and cook up everything and get a function which, and the matrix element will be a function which values in numbers. Function will depend on these w's. Or I can consider this as a function which values on this tensor product. And this function is called conformal block. This function, and from this operator relation on the phi, we get statement that this function satisfies not operator, but ordinary kinetic homologic of equations. I think that people who knows kinetic homologic of equations, what it means, understands this without my explanation. Who don't know probably understand almost nothing from my explanation. So do not.
It's hopeless. So it's hopeless for everything.
I will give some sort of degenerate example, but after the break. And before the break, I don't know, probably we are almost at the time. I don't know when we start, but we are approaching this time. I just say in words that similarly one can define, if I find good chalk here. Okay, I don't know. This is some sort of largest piece. But I mean, this is enough for, maybe this is good for the break. Similarly, one can define vertex operators similarly. One can define vertex operators for Virasoro algebra and define conformal blocks, and this proposition and actually some relative of this proposition will lead to relation on conformal blocks. that let me write it in the manual, that psi of k plus 1 some number okay, some number h and x z is equal to the sum over n psi. Now it depends on the k. Number h will be h plus 2n. Again, x z times z of the b, the same central charge, b k plus 2, k plus 3, special p, and again value z. P is here is something not good. This is okay. If you want, you can consider this a theorem.
This is operator from where to where?
I will explain notation which I used here, and then have a break. We have a relation on conformal blocks. So this p is some very special number. Here is square root of minus k plus 2, k plus 3. Now this. Now let me use a chalk sense. This psi is a conformal. In this case, this is a somehow degenerate, and I will say what degenerate means after the break. A conformal block. For the general, it's difficult to say how many points, or if you want to say vertex separators we have, but you can think as 4. Conformal block for SL2. This Z is again degenerate conformal block for Virasoro. Here's a relation on parameters. This summation should be compared with this summation. So after so we have some sort of intermediate representation, and we have decomposition of this intermediate representation, which leads to decomposition, intermediate representation, which leads to the decomposition of the matrix elements. What else can I comment? I will give definition of psi and z, and so this is some sort of just, I don't know, not honest picture. So definition in this spirit can be done, but I will give another definition. So what degenerate means that we take a vector, we take a limit, and I will state the definition in terms of we take a vector after the break, and this is the resulting relation. And this is quite non-trivial because this function are just special functions. This is nothing. This has different properties, and probably after the break I will explain some application of this relation.
Misha, maybe before the break, let's say a couple of words about the goal of this lecture series. What is this about?
There is a construction of the coupling of vertex algebras, which appears in different subjects. So today I'll speak about this cassette example, and actually after the break I'll try to explain its application to the Penlevé theory, to the explicit formulas for the Penlevé, without some details, but some concrete application. Also after the break I'll try to explain geometric meaning of this relation in terms of a GT relation, what is mean for modular space of instantons. This, because these functions, they in psi are just Nekrasov partition functions. And tomorrow I don't know, probably tomorrow I'll just continue what happened. I plan to talk about another example of this relation. I don't know how to, what kind of answer do you want? Do you want to prove something? Do I want to prove something?
I just wanted you to tell what you meant, how you feel.
I feel it's time to stop.
Can I ask about this relation instance of product? Is it right that in the left-hand side we have something unitary, and in the right-hand side we have something non-unitary?
K is generic, so this is not unitary. Then both sides will be unitary. Both sides will be unitary. If you put k integers, then the sum here will be finite. This value should belong to so-called Katz table.